Turn on the all right. Let's share my screen. Okay. Then okay. I hope you can see the screen now. You see, today is the 4th of February. Our immediate attention should pay to the February 12th, which is your first assignment number 1 due date. Okay, usually it's 4 on Friday. Let me check. 12, or this time it's on the wait a minute. 12 is on the Monday. Okay, so it's like the Monday before the midnight. Okay. And our last tutorial, which is tutorial number 3, will be the 3rd of March after Chinese New Year. Okay, so this is what happened. After that, I will get informed, probably I will get informed by the CC, by our CC, about your final exam study guideline, study guide. Okay, usually I will announce that on the last tutorial, which is the tutorial 3 on 3rd of March. Okay, then what else? Usually your final exam, the average score is quite low. To me, I think it's quite normal, because second order circuit is not as easy as the previous circuit theory 1. So my advice to you is that for your assignment, you try to get as high as possible, preferably above 70 or 80%. Your assignment number 2 is possible. It's very possible to get above 80%. So if you follow the rubric closely, you should be able to get 80%. What I mean is that if you can simulate the result, you can obtain the result, and you have all the 5 sections included. The 5 sections are intro, procedure, discussion, results, and conclusions. Okay, so if you can include all these 5 sections in your report for each experiment, total of two experiments. I think total of 3 experiments, because first experiment we split into 2 high and low pass papers. So totally you should have 3 experiments. So if you can get the one done, I'm quite sure you can get above 80%. Okay, so getting the result, I think it's not so difficult. After that, you need to spend some time to analyze the result and discuss about analyze it, and then discuss and conclude what you have learned in the experiment. Okay. As compared to circuit theory 1, it should be much easier. Okay, not a big deal. Only need to spend some time. So if you still need a video, the recorded video, we need to put it on YouTube. Okay, but today we should look at our first assignment. which due date is the coming soon, about 2 weeks, about 1 week later. Next Monday, really, next Monday. Okay. So see that. So we have total of 3 questions. Just like your final exam, your final exam was somewhat look like this. Your see through second order circuit. By second order circuit, we mean that you should see the RLC in the circuit, and one is the switch open at t equal to 0. The other one is switch closed at t equal to 0. So they should behave differently. Switch open and switch closed is a totally reverse, right? Reverse action. Okay, so you can take you can try to find those similar circuit online, and then get more idea about the second order. Okay, as long as you spend enough time, you should be quite familiar with the second order. And then another topic that you should spend time on is the we call the AC circuit. Okay, and this circuit is quite for this question is quite fundamental to send as your final exam question. Usually, I would expect students to score the AC circuit, and then they try to do as as good as they can be for the second order. But AC circuit is quite it's quite every example is quite similar actually. If you based on the example circuit I'm going to show you later on today, and you compare with your assignment question, and then you compare again with your final exam question, you'll see most of them are quite similar. You just need to follow the steps. If you just follow the steps one by one, step by step, will lead you to the answer eventually. So the AC circuit is the one that easy to score, I would say. Easy to score in the final exam. Because final exam, you have about 2 hours time, I think. I'm not quite sure whether it's a 2 hours or 2.5 hours. But at least you have 2 hours time to complete 3 questions. Okay. Average score is about 50%. We have some students are quite good that can score 70 or 80. Some score 15 or 5 marks or something like that. So it happens every semester. Okay, just to let you know in advance so that you can prepare yourself for your final exam. All right. Okay. After that, what's that? As you know that your online course material is not really complete. You see, it's only based on the some online video or something. Well, it's called a Coursera, I think. It's because this is the new course. In the past, probably you know that in the past we have one course called the electrical circuit and power, and then after MQA visit, the authority visit, and then they want the OpenU to split into two modules, and then because of that they don't have enough time to prepare another set of the PDF course material. So what they did is that they borrow the online material. Okay, the online material is not really complete. Some students still prefer the PDF form. Okay. The first time I looked at this online, I was quite confused also. there are a lot of links to follow. Sometimes you are lost. Okay. But after all, it is you need to follow the example and kind of follow their activities, right? But never mind. Okay. Already, I'm going to share with you the old syllabus, the old course material. But this is not going to be official one. You have to bear in mind. This, the one I'm going to share with you, is not the official for circuit theory 1, circuit theory 2. It's the one that I talked about just now. This is the old course material. After that, they split into the circuit theory 1 and circuit theory 2. But you still can follow some of the material here, because it explained to you some AC circuit. Unfortunately, in the past, the syllabus does not include the second order. You only cover the AC circuit followed by AC power, and then the AC machinery, transformer, and those are electrical stuff, most electrical stuff. Looks like your circuit theory 2 is more electronic, less electrical. So you can see in the past, the syllabus, what you can follow here is the AC circuit. You just follow those AC circuit. When you see those electrical material, I think you can just ignore them. For example, see, until here we still AC circuit, but more towards the AC power, more towards the AC power. Okay, you can see that AC power. I think there's a phasor thing. Let me see. When you scroll the way to the end, now here you can start to see some electrical stuff. Three-phase circuit. This part you can totally ignore. Okay, it's not going to be the part of the syllabus. After three-phase, I think we have transformers, something like transformers. Okay, that's why I think this is the reason why they remove this from the syllabus. Then they convert into the circuit theory 1 and circuit theory 2. They just throw away the transformer, all this stuff, all the electrical stuff. Because of this are part physics and part electrical, they think that it's not suitable for the student like you. That's why they throw away all this. So the one I'm going to share with you, remember, it's not the real course material. It's just a reference. Okay, you can treat it like a reference. Okay, I'm gonna put it here. If you browse to your files, I think I put in the main. I put in the main one. I put it in the main page. In the main page. Home page here. Well, not here. Let me see here. Where is the main page? I think it should be general, right? In general. General is the main page. Okay, I put it here. Okay. Let's put these two reference. I think I should change the name of it. Okay. Not to create confusion for you. I put a reference in front. So take this everything. Okay, first one, this part done. Then what else? All right, let's review back some of the question we have last tutorial. In the last tutorial, we go through some RLC exercises, RLC example. Okay, do you still remember this? Okay, probably I need to share this one with you also. These are the examples. Remember, this time it's a bit difficult for me to forecast to predict your final exam question, because the current course coordinator, so-called CC, right? The course coordinator is the new one. Last semester we have another course coordinator. They replace another course coordinator. So each of them they have their own set of questions, you know. In the past semester, the course coordinator more like to do the inverse Laplace transform. Okay, he like to do the inverse Laplace transform. So but this time this CC doesn't care about the inverse Laplace transform. So if I realize that you need to learn some inverse Laplace transform, I will try to give you some exercises also in the next tutorial about the inverse Laplace transform, like this. It's more like mathematics more than a circuit, I think. To me, I feel like more than mathematics. That means your question based on this one. It give you this equation, ask you to do the inverse Laplace transform. Looks like a mathematics class, actually. So this is your answer. Where is it? Oh, this example. This answer. Incomplete answer. Where's the complete answer? Looks like can't find the complete one. This is one example. Determine the inverse Laplace transform of this function. So you go through all the steps. Eventually, you will get the answer like this in the time domain. Okay, but this time around, I'm not so sure whether this is going to be part of your syllabus or not. Feel like this one is more mathematics than the circuit theory. Okay. So let's come back to the assignment number 1. Assignment number 2 looks like the not so relevant to the second order, right? Assignment number 2 is the lab, and then we have transformer also. You can forget about lab number 2. I think for the final exam, I don't think they will come up in the final exam. So you should put all your time in the second order circuit. Okay. So this previously we have one example looks like this, the RLC circuit, the very classic question with the 12 volt and 3 passive components. And then when we apply the power, we try to determine the current as a function of time. So to do that, first we need to use a KVL to obtain the basic equation. Since the equation consists of integration and the differentiation derivative, with our ultimate answer is something look like this. I is the function of time, I at the time domain. Okay, so we need to go through we need to use the Laplace transform to convert this one into the Laplace frequency domain. So this is what we get. Okay, after we convert, and then we try to reassemble everything to follow the Laplace function, the S plus alpha. Okay. Eventually, when we can convert the Laplace equation into something that looks like Laplace, belong to Laplace function, then we just replace it. S plus 1 become e to the minus of t. and then minus 4 factor out already, 4 and then e to the minus 2t. As long as you can come to this step, then you can do the inverse Laplace transform. So this type cut is quite time consuming for the final exam. I agree that in the final exam it's quite stressful also. From this step, you need to all the way come to the last step, and then you need to come to this step so that you can easy to convert into the Laplace, to do the inverse Laplace transform and obtain the last result. It's quite stressful actually. With a limited time, if it's a homework, I think it's okay. But with a limited time, let's say 1 hour time, sometimes it's quite stressful. Okay, so this is the first example you have. And then we also look at the question number 1. Question number 1 is also very similar to RLC. But initially the C has no function. Initially when the circuit is closed, yeah, this one has a function also. This one has some voltage here. When the switch open up, this part becomes irrelevant, and then you have this circuit now, RLC. Okay. So it's really similar to the RLC circuit. RLC, but before that, before the time equal to 0, we call it time less than 0 or 0 minus. We need to determine the initial condition. This is the first difficult part for the student. That's why I gave you one exercise on the initial condition. If you cannot get the initial condition right, the next step you're not getting it right, you're getting it all wrong, right? If the first step is wrong, the subsequent steps all will get affected. That's why this is the make it more difficult, okay? Because the difficult part comes first. That is the initial condition. So I think it's worthwhile for us to relook again on how to determine the initial condition for the circuit. So you look at the circuit here. Initial condition, when the switch is closed before time equal to t, we have the current flow through here. The current can flow through R, flow through the L. The current can flow through the resistor, but the current cannot flow through the capacitor, right? The current can only charge the capacitor to the fully charged. Then it will stop. Then the current will stop. Okay. The current in this path through the capacitor will stop when the capacitor is fully charged. But the current will flow through here continuously. You know. That's why we have two conditions. Looks like. Okay. First, when the time less than 0. When the time less than 0, the switch is still closed. Okay, we have a circuit like this. And since for the long time, when the time is not transient, it's a long time, the inductor and the capacitor, they're almost like the transparent to the circuit. The inductor will most likely behave like a short circuit. That's why it's a short circuit here. And because this is a fully charged, the problem here is not a problem. Sorry. The situation here is that this capacitor and this resistor, they have a common nodes. When they have a common nodes, means whatever voltage across the resistor 1 ohm will be the voltage across the capacitor. Because this is already fully charged, this will be fully charged in less than 1 second. So the whatever voltage here at the output, So the voltage is placed near the capacitor. V plus minus is the output voltage here. Since the circuit is closed initially, so this also means that the output voltage for the resistor also, so that we can just move the V out to the right hand side. So the output voltage is similar to the resistor output, with resistor voltage or the voltage across the resistor. So for this reason, this has no function actually, because we just measure the voltage across the resistor is similar to the voltage across the capacitor. Okay, because this is fully charged already, current becomes 0. When the thing is fully charged, the current will reduce to 0. Initially, the current is at maximum, and then the current will come to 0. Okay, so this thing we have to assume that when the thing closed for a long time before you open, this is already fully charged. This is already a closed circuit. So we need to determine the voltage at time equal to 0 minus before the switch open. Current at time equal to 0 minus before the switch open. Okay, so this circuit looks rather simple right now. After we make our assumption, this becomes short circuit, this becomes open circuit. We just reduce the circuit down to 2 components only, 5 ohm and 1 ohm, and they are both of them are just resistor, so it's very simple circuit. In this case, this circuit more function like a divider, voltage divider. 24 volt to divide into 5 ohm and 1 ohm. So you can first calculate the maximum 6 ohm, and then 1 ohm will get 1/6 of the 24 volt. 5 ohm will get 5/6 of the 24 volt. This is how how the thing works. Voltage divider. All right. So the answer. Hey, so I already give you the answer already. But I think I should do that. I should give you the answer, so that you are not you know, start with the wrong foot, I think. So I want you to start with the right foot. Okay. So I have to let you know the initial condition for this one. Okay, I will let you know the V out here. Let me make clear to you, because I cannot help you 100%, but I think I should help you at least 30% and above, so that you continue on from there. Okay, so let me copy this, and last time I didn't give the answer, right? But this time I'm going to help you about 30 to 50%. Okay, so you listen carefully. So this is going to be your Q1. Okay. Q1. So this is going to be, the answer it is, spend a few more pages. So the answer for the initial condition is very important. Is 1 over total resistance 6 times 24. It means 24 divided by 6. 4. As for the current is the, I think you should know, right? The 24 watt and 2 resistor. So the current is I2 V over R. In the final exam, if you do this, your score, let's say, out of 10 marks, probably you'll score about 2 marks already. 6 ohm. That means it's 4 amperes. Just nice, 4. Okay. In the final exam, you can determine the initial condition, you score about 20% already. So after this, your next step is what? Your next step would be to write the KVL, but this time we also need to determine the after the switch open, when the switch open is time greater than 0. Okay, when the switch open, just now we focus on the before the switch open. Now we focus on the switch open. When switch open, this one is no longer relevant. We just have this circuit on it. So we redraw the circuit like this. Okay, we place our voltage output here. And now it looks like RLC. Basically, it just looks like RLC. Okay, RLC circuit. And then for RLC circuit, we first need to decide whether this is the overdamp or underdamp or something. Okay, we need to determine whether it's overdamp or something underdamp. Therefore, we need to apply this formula here. Alpha, we need to find first. We need to calculate the alpha and the omega, the frequency. Okay, so this is already fixed for RLC response. The response for this circuit, alpha is R over 2L. So if you calculate this one, because the value already been given, you just substitute R with this 5 ohm, and then you should able to calculate this. And then you base on this formula, you place the alpha in plus minus, and then you will get two answers. One is for the plus, one is for the minus. Okay, one is for the plus, one for the minus. Because we plus minus here. And then if you find that the alpha is greater than the omega, then it's become overdamp. Then this circuit is overdamp because the value determines the condition. So if the value you get, I mean these 3 values, resulting in the overdamp, then you need to the final answer will look like this. 24 volt is the initial condition plus this part and another part here. Okay, this is going to be your final answer. And then your S1 and S2 is already calculated. You just need to insert it into this equation. If it's overdamp. Okay. And let me see. Let me give you an idea whether this is the overdamp or underdamp. Okay, I think I can help you. This one I can help you. Okay, I think you should know also. This case is the overdamp. Okay, for this example, for this not for this example, for this question is overdamp. Is overdamp. Okay, hold on. Since, okay, you need to calculate this one, right? You need to calculate. Okay, I will help you every step. Since alpha is greater than omega 0, the formulas are here. Okay, but you need to calculate. Okay, how come disappear? Okay, since it's greater than 0, we have the circuit. We have the overdamp. It's called overdamp natural response. Okay. Then our final question, our final equation, the time domain, in the time domain, going to be look like this. S1, S2 already been determined. So what is left is the A1 and A2. How do we determine A1 and A2? So last time we stopped here, right? Last time we didn't talk about A1 and A2. Okay. How about right now we start talking about A1 and A2? Last time we stopped here, and then I want you to determine the VT A1 A2. Then I say the IT is usually take the VT differentiation. Then you can get IT. Once you get the VT, you can get the IT. Okay. So now is how do we determine A1 and A2? Okay. So what I can help you is like this. Probably I'm going to stop. I'm going to stop after this step. Okay. This as far as I can go right now. Okay, so we go. What we need going to do right now is to determine A1 and A2. We need to find more equation to help us. Okay, we need to find more equation. And we know that our final equation looks like this. Our final equation looks like this. This is our final equation. Okay, yeah. This is the final equation. To find the A1 and A2, we need more equation. Okay, so the first equation we're going to use. The first equation we're going to use is using the initial condition to find the A1 and A2. We probably need two equations. Okay, let me help you for the first equation. For the first equation, first use the initial condition. Vt V at 0 is equal to you already know. S1 you already know, right? But I want you to calculate yourself. S2 is already been determined. But I don't want to show you right now. I want you to calculate yourself. So the V0 we already determined to be 4 just now. Is 4. So just put the 4 here. Okay. So when the time is equal to 0, t equals 0, this is the t. If you put the t inside here, this is what you get. The whole thing here multiplied by 0 is equal to 1 actually. E0 equal to 1. E to the minus of e to the 0 is equal to 1. Okay, whether we can use a calculator to determine this or not. Yeah, let's try. don't think we can do it here. Yeah. Let's use the symbol. So we use the calculus. Yeah, let's try. There's no E here. E power 0. Go. Equal to 1, right? Equal power 0 equal to 1. So this the whole thing become 1. So we have A1 and A2. So this is the very important information. We have one important information. We have two unknown here we need to determine. We now have one equation. So we move this one over. Okay. We can further simplify the equation. How about the next equation? Because this is just one equation only. For the second equation, we need to use the second equation. We use initial condition. We use the initial condition I when t equal to 0. Okay. So I will stop right here. When I at the t equal to 0 is equal to 24. Sorry. This is given as Vt. Okay, but for the IT is actually C D V0 or condition is 0. Okay. Then to do this, you will get an answer here. You get an answer. Okay. I go to 0. Is equal to 4, right? Equal to 4 ampere. So how about this dV0? That means you need to try to figure out how to do the function. Take this function. Take this equation here, V0. Okay, take this equation V0 and do the derivative. And then you will get the next answer. Okay, you'll get the next answer. Okay. After that, then what you do is you take the dV0. After that, you take the dV0. Okay, you obtain the answer right just now from the previous step is equal to the after you do the derivative, you'll get the answer here. Don't know how to review this. You will get something like the first part here minus another part. So you have A1 inside. Yes, A2 inside. Remember when you replace the 0 into the function t 0, you go to 1. You won't see this part anymore. You won't see the exponential part anymore after you replace with the 0. Okay. But first, you need to do the differentiation. You need to do the differentiation. Okay. For example, let me show you example. Let me show one example. You come back here. You do the differentiation here. D dx, right? So the x is our t. We just replace the t with x. Let's say they have a, right? A1. Let's say A1 is A, A2 is B, right? And then you have E to the, let's say you find to be minus 2t, for example, okay? Minus 2x, because of dx, right? Dx, minus 2x. And then you can do the differentiation or the derivative. So this answer. Okay. So they need to, this is the dv0 dt, right? dv0 dt. Now replace with the dx. Right here. Okay, first you need to take this function. After you find s1 and s2, you do the derivative. You do the derivative and then you use the 0 as the time. By doing this, you will eliminate the exponential part. When you replace the exponential part with the minus 2 times 0, for example, so some of you may not understand this. Let's say you have an exponential to the minus 2 times 0. Of course, you'll get 1, right? No matter how much you multiply, you still get a 1, right? So the 2 is not relevant anymore, because anything multiplied by 0, you get a 0. So you still get a 1. Then what that means is that you totally eliminate the exponential part. You're down to only A1 and A2 only. Okay, so this will become your next equation. This is your first equation, and then this is your next equation. Okay, so this is going to be your next equation. So this something equal to something inside got A1 minus something inside got A2 is going to be your equation number 2. So at this step, I don't need to elaborate further. I think you should be able to figure out the A1 and A2. A1 and A2, two unknowns equation with two equation, simultaneous equation, you can solve for the unknown already. Okay, this is a basic calculus. The basic algebra. Using the algebra, you should be able to do that already. Okay, using algebra, you should be able to do that. Let me give you a quick example. 2x plus 1 equal to y. Another one is and then comma. Another one is x plus y equal to 10. We have two equations, two unknown. Then we should be able to figure out the x and y. X is 3, y is 7. Two equations, two unknown is enough to figure out the answer. Okay, so just like this one, two equations, two unknown. So what this tells us that by looking at this, I think you can see that the initial condition is so important. Because we understand the initial condition, we can just follow the normal step, do the derivative, and this one also do the derivative. This one we just put it in, substitute the t equal to 0. We obtain the first equation. The next one that we do the derivative, and then we also take the initial condition 4 ampere, and then we can figure out the next equation. That's why the initial condition is so important. If you cannot get this one right, the next step probably you'll get it wrong. Okay. That's why if you look back to the our previous example, I have another exercise, right, to train you on the initial condition. Here is another example. Okay, the thing reverse. You see how we figure out the initial condition? This one. Okay, if you still not so clear, you can refer back to this example. Okay, this how I'm going to stop here. Okay, I'm going to stop here uh, because I already almost showed you 50% already. Okay, I already showed you 50%. I think you need to work your own way. Okay, let me save this one first. All right, after a break, we will look at the question 2. I'll give you until 50% also. After the break, we will look at the question number 2 here. Very similar, right? RLC also, RLC. Okay. We will look at how to find the complete response V and then I for time greater than 0. When time greater than 0 is closed. Okay, I'll give you, then we take some time to cover this also. We have until 4:30, now the 3:30. So 1 hour only. Okay, so after that we're going to use 30 minutes here, 30 minutes here. Okay, let's take a quick break right now. Meanwhile, let's look at, it looks like somebody posed a question. Okay. All right, we take about 10 minutes break, then we come back, continue on our question number 2. All right, let's come back here again. Okay, let's copy first. Let's what is it? Let's copy this to our document. So this is going to be Q2. Okay. Okay, when we're dealing with the second order circuit, most likely is RLC. Okay, this is a side note only. Usually when we're dealing with the second order circuit, okay, let's type it in. Usually when we're dealing with second order circuit, especially the RLC, then we should have prepare for series and also parallel RLC circuit. Okay, there are two possibilities. One is the series, one is the parallel. So in this case, most likely, most of the time we've seen is the series. Okay, but you need to prepare for parallel also. The first step usually is to determine the initial condition. As for the question number one, we just based on the initial condition, then we can from there we can figure out the whether it's overdamped or underdamped. We calculate the alpha and omega and to determine it's overdamped or underdamped. Okay, then we determine whether it's overdamped or underdamped circuit, so that we can apply the Lagrange equation. Usually, when we come to the third step, what we're going to deal with in question 2, we may need to turn off the independent source. In the RLC circuit, usually we can see one independent source. We may need to turn off the independent source in order to figure out the the unknown. Most of the time, the independent source is the voltage source, right? Okay, for example, the voltage source. To figure out the unknown. So you're going to see in this example, in this question number 2, where we on the third step we may need to turn off the independent source to figure out the circuit. So you need to understand why we need to do that. Okay, let's observe. Let's observe why when you come to the circuit 2, when we come to the question 2, we need to turn off this 12 volt. Okay. So first step, I want you to try out the step number 1 is to figure out the initial condition. Okay, I can give you 50%, and then you try to figure out the rest. For the initial condition, the circuit is open. Part is open. It's closed at T00. That means before T0 is open, which means the 2 ohm here is not relevant. Okay, let's draw the circuit. For the initial conditions, we have 12. We mean the T less than 0. We have 12 volt here. Okay, and then we pass through the 4 ohm resistor. And this one, since we did assume that before the t equals 0 for a very long time, the L has no function at all. It's just a short circuit, just a short wire. Because the L only active when we have a change of current. So since we assume the before t equal to 0, for a very long time, the switch remain open for a very, very long time. The L has no function, okay? And then this part also has no function. So what we have is only like this. Because this capacitor, as I mentioned before, capacitor, when this one is fully charged, it becomes open circuit, okay? When it charged to the 12 volt, we have only one independent source here. This source that doesn't affect by any component here, so this is called independent. So when the capacitor is fully charged to 12 volt, so this circuit will remain open. So what we can predict. This is the initial condition before t less than 0. Okay, so can you figure out the voltage here at 0 minus, also the current at 0 minus? Okay, can you figure this out? So I give you a moment for you to think about this. Then we'll proceed to when the circuit is closed at t equals 0. Okay, so the answer is very obvious. Let me see here, because it's quite quiet here. Maybe whether the mic is still on. And the recorder. Okay, this is very obvious. This looks like the open circuit, right? Totally open circuit. The current cannot flow, right? It's not a closed loop. There's no current flow. That's why the voltage here is going to remain as voltage here, right? So the voltage here is 12 volt. Since no current flow, so this is a 0 ampere here. So this part is rather simple. Right, let's proceed to step 2. Step 2, we try to figure out what is the condition when the time is greater than 0. When time is greater than 0, what will happen to this circuit? That means we have a full circuit already. Okay, let's draw the circuit here. Let's draw the circuit again. We have 12 volt, 4 ohm, another inductor here, and then another resistor here. Okay, another capacitor. So this is after the condition after the switch closed. We have 2 ohm here. 0.5 farad and 1 Henry, 4 ohm. Okay. Now the V out is still here. The V is still here. Okay, the V is still here. So this 2 ohm and half farad, they share the common node. These nodes are common, and these two, the above nodes, are also common. So the voltage is the same. So this voltage, as you know, when for a very long time, when the switch closed for a very long time, this one also become a short circuit. Okay, and the voltage, what will happen is that the voltage here, the V for the V plus here, eventually the voltage will charge to the full voltage here. Wait a minute. Here. So we have 3 conditions. Sorry, we have 3 conditions. We have 3 conditions. V0 slightly plus only, slightly plus. That means the moment that the switch closed for, let's say, a microsecond or millisecond, what is the voltage here? The voltage will still remain as a 12 volt. Even though the voltage will go to share by this 2 ohm and this 0.5 farad. But this 0 plus here means it's just a slightly over the 0. This is a timeline. So this 0 is slightly here. Okay, it is at this point here. It's just slightly above 0 only. So by right, we only assume it's 12 volt. Okay, because if we leave the circuit for a very long time, I think this by assuming like this, I think it's incorrect. Okay, because usually when this means it's very for a very long time, I think I should change my assumption here, because we have 3 conditions now. This one should be declared as 0 slightly plus only. That means when the switch code is 0, it's slightly just some microsecond later, V0 plus still 12 volt. Okay, because for a very long time, this one is already a voltage going to be shared by 4 ohm and 2 ohm. It's going to be a voltage divider. But when you consider only the 0 plus only, just a moment after the switch closed, it still remains as 12 volt. Okay, then the I at 0 plus, slightly 0 plus, is still remain as 0 ampere. So why we want to go through this step actually? What is the meaning of go through this step? Is to help us to figure out the capacitor voltage here. Is to help to figure out the capacitor current. Okay, we need to figure out the capacitor current. Capacitor current at 0 plus. Okay, we need to obtain one value from this C equals 0 plus. Okay, and then as we know, the current, the main current flow through the 4 ohm and 1 Henry. This is the main current, and the current was split into two. One into the 2 ohm. Let's call this one I2 ohm. Another one current was split into the capacitor. Let's call this one IC. Let's call this one IR. Okay, IR. IR 2 ohm. Okay. So the the total current I here So total current I 0 plus right here, the moment after the switch close, is going to be the IC plus the IR here, I2 ohm. Okay, the current split the two. Okay, then we, based on our assumption, initial current, even though the current can flow through, right? Initially, the current should flow through it really, really quickly. But you have to understand that this inductor, whenever the switch is closed, the inductor try to limit the current flow. You can observe this one with the something we call the RL circuit. Let's call the transient RL circuit. Let's try this one. For the common RL circuit, the behavior of the inductor is looks like this. You can have a look at the initial current. Is it the one? Yeah. RL, right? RL. Yeah, RL. Yeah. You can see it initially the current here, the current being the blue color, when the time first close at 0, initially the current is 0. This is because of the inductor is trying to limit the current flow. Okay, when the current try to flow through the inductor, the inrush, we call the inrush current. When you try to flow through the current in a very fast manner, the inductor try to limit it so that it will initially it will become 0. Then you're going up very, very quickly to reach the maximum, right? But we are talking here. We are talking the point near the 0 here. It should be 0. Okay. So for this reason, that's why the initial current here, the I0 plus here, is actually 0, based on the behavior of the inductor. RL, because this circuit is RL, right? So the it's quite safe to assume that the initial current when the switch closed, initially is 0 first. Okay, 0 equal to. But if you refer back to this circuit again, before the switch closed, we have another circuit, right? Even though this is open, but it could be a charge already stored inside here, right? It could be a charge stored here. Okay, that's why we try to figure out the IC at the time 0 plus here, IC 0 plus here, plus I2 ohm. I2 ohm, if you treat this one as a short circuit, the current is going to be the voltage at 0 plus divided by the 2 ohm. Okay, I mean this voltage across here, the voltage across the 2 ohm divided by 2 ohm is the current. Okay, so this the value we know already. Therefore, IC at time slightly above 0 is equal to 12 over 2 ohm is equal to 6 ampere. This part is quite difficult actually. This part you need to understand the behavior of the RL and the initial condition of this capacitor. Initially, the voltage here is already charged to 12 volt. It's open circuit, but this is fully charged. Fully charged, when you close the circuit, the 12 volt going to be the 12 volt across the resistor going to be the current, determine the current at 2 ohm here. Okay, and we know that the current initially, the main current here, the main current should be 0 based on the RL behavior. Based on the RL behavior, the main current here should be 0 initially. This one is initially it has 12 volt, already have 12 volt here. So this 12 volt determine this 2 ohm. So from there we can determine the capacitor current at initial stage. Okay. So this part is quite difficult, and provided you need to understand the RL first, the first order circuit, the behavior of RL. RC is quite similar actually. RC and RL, they are quite similar. If you check RC, it's quite similar also. If you check RC, you see the exponential curve is about the same. Okay, it's about the same here. Initially, it starts from 0, but this is understandable. Only the RL circuit is quite new to the newcomer, because when you first close the switch, initial current should be 0 because of this inductor. Try to limit the current flow, limit the inrush current flow. So this is the second step. You can also consider after the initial condition, second step when the switch closes, and then the third assumption, of course, is when the time much greater than 0. Eventually, we have. Let me see. Oh, we don't need to do that actually. We don't do that in this example. We only assume up to this stage only. Okay, but I still need to guide you through some of the important steps so that you can follow through the remaining steps. All right. Now, since we already figured out this one, okay, so the next one, we try to figure out the current when the switch closed for a very long time. Okay, when the current switch closed for a very long time, this is what happened. I need to copy and paste this one. Put it back here. Okay, for a very long time, when the time is much greater than 0, for a very long time, we will declare it as I infinity for a very long time. Okay, when the switch closed for a very long time, the current of the whole circuit, I mean the main current here, because this one will become open circuit after it's fully charged. Then the current is equal to the voltage divided by the total resistance. Okay, it's 12 volt over the 4 plus 2, because this open circuit already for a long time. So we have only, this one becomes short circuit, become a short wire. So for a very long time, we only have 4 ohm and 2 ohm. 4 plus 2. For a long time, we have become back to 2 ampere. Initially, when the switch closed with 6 ampere, then immediately after a while, you reach 2 ampere. Okay, how can we utilizing this 2 ampere for the for more information we can extract from this circuit? The other one is the voltage also. What will be the voltage output for a very long time? the voltage across the capacitor here for a very long time is equal to the current, because the same current flow through the 4 ohm and 2 ohm, right? So it's equal to the current times the resistance 2 ohm. Okay, so it becomes 4 volt. Okay, so this you can say all these are the initial condition. All right, so now let's go back to the again. I mean this circuit when the switch is closed. When the switch is closed, we have a main current flow through the 1 Henry. This is the main current I, and then the current is split into the 2 branches here. One is the 2 ohm, one is a capacitor. We declare as IC. We call this one is I2 ohm. So we can rewrite again. Okay, the current is equal to the voltage. The voltage is between here and here. Okay, so the voltage is this point and this point is similar. Voltage at this point are they common. So the voltage also here. Voltage across the 2 ohm is equal to the I2 ohm plus IC for a very long time, right? IC. Okay, let's try to extract more equation so that we can figure out the subsequent steps. So the I, the V, this one is the V over 2 plus C is the 0.5, right? 0.5. IC is a C dV dt, right? IC C dV dt. So this one C times dV dt. Okay. So we can for a very long time, this is the equation we could get. V, the voltage here. Okay, this is what we get. Another equation we can come up is to turn off the power supply. When we turn off the power supply, when you remove the power supply, we get a circuit like this. Okay. We have the same I flowing through here. We have 4 ohm, 1 Henry. Okay. So the voltage here, let's do the KVL here. 4 ohm, 4 volt is what? It's a 4 times the current I. It's the voltage here. The voltage here is L dt plus the voltage here, the V. This is another equation we can come up. This is 1. This is 2. Okay, this one is still have the 12 volt. We still have 12 volt here. This one is without the 12 volt. We turn off the power supply. Okay, then we obtain this equation, another equation. When we turn off the power supply, let's focus on the current flow here. Then we obtain another equation. Okay, and right now we need to substitute the I into here. So this step become really difficult, right? After this, I think I'll stop until this step. The remaining step will be much easier already, because I already lay the foundation for you. Okay, the subsequent step will be much easier. Okay, so let's substitute the I into here. This part is really, I have to say, this one is a bit challenging essentially. Substitute 1 into 2. Equation 1 to 2. So we have 4 times V over 2 plus 1/2 dv dt. Okay, plus L. L is 1, right? L is 1. 1 d dt, and this part V over 2 plus half dv dt. Okay, and then plus V equal to 0. Okay, so let me solve this one for you. Hopefully you can carry on from here. So 4 times this one become 2V plus 2 dv dt. 1 times the integration of this one dv2. Okay, become half dv dt plus half d2v, because 2 times, right? 2 times d2v dt square. Double derivative, okay? Double derivative to get this. Okay, then plus v equal to 0. So probably you will ask why you need to go through all these two conditions here, assumption. One is the close for a very long time. One is the turn off. Because we need to figure out the they call the characteristic equation. From there we can determine, because this is also another underdamped circuit. Okay, but we cannot follow the previous example, same example. But because this one is much more complicated, unlike the question 1. Question 1, when the switch open, it becomes open circuit. When the switch close, we have to do this two really you know, how the passive component will behave is unlike the equation 1. This one is more complicated, okay? Because we're going to figure out the change of current, change of voltage. When the moment you close the switch, the current here, the voltage here. Okay, that's why we need to these two equations to help us figure out the they call the characteristic equation. Okay, so when you reach this step, okay, when you reach this step, you need to do the derivative. Okay, but we can simplify it now, because we have half d2v, right? So we multiply by 2. We multiply by 2. We rearrange everything. We get d2v dt squared plus 5 plus 5 dv/dt. After you multiply by 2, multiply by 2, 2, 2, 2, right? Then 1 plus 4, you get 5. And then plus another 6v, 2v plus 4v, 6v, equal to 0. So this is called the characteristic equation. From here, translate to something we call the characteristic equation. It becomes x squared plus 5s plus 6 equal to 0. So this slowly approaching the Laplace domain actually. Okay, we somewhat convert this one to the Laplace domain. Also, from the previous step, okay, I haven't actually figured out the S1 and S2 yet. Okay, we need to figure out the S1 and S2. So from here, actually from here, this S is what we want actually, S1 and S2. If you solve for this equation, you will get S plus something and S plus something, right? S plus something and S plus something. Then this something here is our S1 and S2. Okay, and then after that, I can show you that our final equation is like this: V T is equal to A minus S1T plus B e to the S2T. Okay, this is our final equation under them. Then how do we continue from here? Because I already showed you 50% already now. How do we continue from here? From initial condition. Well, now we left very little time for the last question. Probably I will continue this one on the WhatsApp. Okay, I'll continue this one on the WhatsApp. But here, until here, I think I have to stop here. You can refer to some online notes. Probably they will cover this part also. After this, we need to, of course, now we need to determine the A value and B value, just like a previous question. We need to determine the A and B unknown. From the more equation, we need to come up with more equation to figure out the A and B. For this one, we can based on the V0. Okay, I give you some highlight, some tips here. We can use the V0 to figure out one equation. Okay, and then after that, we use the dv/dt, okay, to figure out another equation. After you done these two, you will find your A equal to something, B or something. You are actually close to the final answer with you. Usually you get the final answer because S1 and S2 is coming from this characteristic equation. Okay, S1 and S2 is coming from this characteristic equation. You just substitute in here A and B, A and B. One equation is coming from here, another equation is coming from here. Okay, I cannot review 100%. Of course, I only review up to probably 50%. So you need to do this part to obtain one equation here, another equation here, and then you should be able to figure out A and B. Okay, then you get the VT. Okay, and then for the IT, let me review the IT also for you, because you need to define IT also. For the IT, you can, based on this equation, IT is equal to the VT over 2 plus the half dV/dt. You need to take the V, do the derivative, multiply by half, and then the derivative, the VT divided by 2 is become your IT. Okay, so this is the VT and IT. The VT and the IT for this question number 2. Complete response V and I for t greater than 0. So I would say this part is a bit, this part here, especially this part, is not very common to see actually. One is to based on the circuit closed for a very long time. The other one is take the source away, removing the independent source and try to figure out another equation. Then we substitute the I into here to find the characteristic equation. But this is a good practice for you actually. After you have seen example like this, in the future, it may help you to solve some other question also. When you try to figure out the unknown from the circuit. Okay, but we have to stop for a while. So before we go, so I'll stop until here, because I cannot show you 100%. I need to show you here. You need to figure out this step. Okay. Right now we still have one question to talk about, which is the question number 3. Okay. I want to make it clear before we begin this question. I want to make it clear to you that something is quite important. I need to make it clear, because every time student will get this one wrong. I think it's my duty to let you know, before you make that kind of mistake. Actually, this phasor diagram for this part 1, part 2, part 3, and part 4, they are quite common. They are quite standard. The one I want to talk about is this step number 5. The phasor diagram, what we are talking about here, is the phasor diagram of the impedance. Okay, not the power, not the phasor diagram of the power. Most textbooks talk about the phasor, because it didn't mention why this is a phasor diagram for impedance or for the power. Actually, it's for the impedance. The answer is in impedance. Okay, that means here is your Z. Here is your XL minus XC. Because from the previous step, you calculate the total inductance and total the capacitance. So this is your R. Okay, you need to draw this angle here, theta, is coming from here, the phase angle. Okay, this one is, I want to make it clear, is the impedance phasor diagram. It's not the power phasor diagram, right? So if you search online, if you search for phasor diagram, you may come across most likely is the power phasor diagram. Most likely is the power, like this. Voltage also, voltage phasor diagram, and most likely is a voltage current also. But this time because most students they gave the answer like this, current and voltage phasor diagram, but the answer actually is in the impedance. That's why I let you know that, make it clear that the part 5 is draw the impedance phasor diagram. So if you put impedance here, So you get something like this, right? The L minus C, L minus C, VL minus VC. Now what we're looking at is the XL minus XC. So yeah, below the voltage, what we are looking at is this one. XL minus XC. Okay. So take note of this one. And then before we attempt to solve this question, I have provided you a exercise. So I want you to take a moment here to understand it. Later I'll provide you an answer. So this is you can say this is the preparation for the answer for the question. Because this question only consists of two passive components and the power source in this format. You need to find the VT and IT also. Because here is provided is the voltage and the function of time. Right? In this format. And your question actually is a bit different. Okay? It's 100 volt. It's given in this format. 100 volt as some frequency. But this example here is a frequency component is already here. When you understand this component, you understand this question, probably will help you to understand the power in this format. Okay. So this is how to calculate the impedance for each passive component. Okay, take a moment to look at this. Okay, later I'll show the answer. Let's take a break. I need to take some water. All right, I have to continue because the time is already over. I need to quickly cover this. So you see here, one current flow through two components, and the output actually is the voltage of the capacitor, but only one current flow through these two components. And this is the maximum voltage cosine function and the frequency of 4. Omega is equal to 4. Okay, so this is some simple equation that we may use later on to calculate the impedance for each component. See, in this case, we only R and C. That means we only need the R and the Z impedance for the C. So the first step, of course, is to determine the total resistance. Z is equal to the 5 ohm plus the 1 over J omega C. So omega actually is 4 based on the equation here. 10 cosine 4, 10 cosine 4t. This actually is a cosine omega t. So 4 is omega equal to 4. Okay. C is 0.1. So after you calculate this one, the Z you will get in the rectangular form 5 minus J 2 plus 2.5 ohm. Okay, you'll get the first output here, the total impedance for the whole circuit. And then with the total impedance, we can calculate the total current. Total current is equal to V over Z. So the V is, we extract from here, is a 10 at 0, because there's no phase shift. There's no plus something or minus something. There's no phase shift. So the 10, 0 at this divided by 5 minus J 2.5. Okay. So the current you get is in the polar form is 1.789 over at an angle of 36.57 degree ampere. Okay. So the question asks for the current as a function of time, the voltage as a function of time. So the current as a function of time, since we have the current already, so the current as a function of time is equal to the value here, the current, the main value here, 1.789. Okay, because the input is a cosine function times cosine 4t, and then this is the positive value, so it's plus 26.57 degree ampere. So this is the function for the current. Straightforward, right? Quite straightforward. Provided you understand the how to convert from polar to rectangular. Probably for this question, you need to come to this website. I visit this website quite frequently. It helps you to convert. It has a calculator helps you to convert from polar to rectangular. You just need to key in the, let's say for the rectangular to polar, you just need to key in this 5 minus 2.5. You just key 5 minus 2.5. Then you just click here, you'll give you the answer in the polar form. Because you only can divide using the polar form. When you do the plus and minus, you can use a rectangular form. Division and multiplication need to use a polar form. Okay, this is the fundamental. One more time, okay. When you do the calculation, it involves this imaginary component. When you do the division, you need to both in the polar form. Okay? Division or multiplication, both must be in the polar form. When you just do the plus and minus, you can just remain as the rectangular form. So this is a rectangular form. Rectangular looks like this. Okay. So another question is to ask for the VT here. VT. Actually, the VT is the capacitor voltage. So the VT actually is the capacitor voltage T. For this, we need to determine the capacitor voltage. So the capacitor voltage is equal to the main current times the capacitance impedance. Okay, from here, capacitor impedance. So after you multiply these two, you will get 4.47 minus 63.43 volt. Okay, therefore the voltage as a function of time is equal to 4.47 cosine 4t minus 63.43 volt. So if you compare side by side with the current, you can see the current is leading. Current is plus 26.57. So current is plus 26.57 degree. The voltage is minus 63. The voltage is minus 63.43. So if you look at the timeline, let's say we have this voltage here. Let's say we have the waveform voltage here. Oh, wait. Okay, let's say we have voltage here. The peak. Oh, the thing messed up already. How come this one come here? Never mind. The peak is oh, everything messed up already. Let me see if I can reverse that. Oh, what happened to this software? Messed up already. Never mind. The peak, the peak for the voltage is here. 4.47 cosine function. Okay, the three cosine functions will start here, right? Never mind. Okay, and the peak is here, and then the degree, the current just now is plus 26.57 degree, right? So this is the voltage function. Current function, the current is much lower, right? The current has been erased already. 1.7789. So the current is here. The current is here. It's somewhere here. I put the dotted line here. This, you can see they are out of phase. So this is the current. The current peak is at the 1.789. 1.789. And then the phase shift here, current is leading by 26, voltage is lagging by 26. So the total phase shift is 90 degrees. 26.57 and 63.42 is 90 degrees. So the current lead the voltage. Current leads voltage by 90 degrees. Because this is the capacitor circuit. You see everything overlap. Strange that this software, I think this software is crazy already. Everything overlap. So the current, because this is the capacitor circuit. In the capacitor circuit, the current will lead the voltage by 90 degrees. In the inductor circuit, the reverse. The voltage will lead the current by 90 degrees. Because if you consider the circuit like this, right, the voltage will take more time to charge up the capacitor, where the current just flow through, right? The current can flow through, but the voltage will increase slowly. Yeah, that's why the voltage will slow down. The voltage is the one behind the current. This is a voltage. This is a current. So the voltage is behind the current. Current go first. So that the difference here is 90 degrees. So usually sometimes from the data we can confirm our answer is correct. When we calculate the answer here and here, we can confirm that the answer is correct. Strange, this software sometimes it doesn't behave abnormally. Let me see if I restart again. They restart again, everything back to normal. But the part disappeared. Yeah, man. Okay, now look at the real question we have. I need to give you some guideline also. Just now here. So for the first part, this is what you should do. Let me give some help here, so that you can get somewhere like 80 to 90% for this exercise. So for the part one, what you need to do is, actually I haven't explained to you what happened, right, to this circuit. Let's start from the circuit, okay? Actually what happened is that this circuit looks like this. It has three impedances. First impedance consists of the inductance and the resistance. Inductance and resistance. This is the first impedance. And then followed by the second impedance, inductance and resistance. Another inductance and resistance. This is the second. The third one is the capacitance and the resistance. The third one here, capacitance and resistance. Okay, they are all connected in series. And then both of these three impedances are powered by 100 volt and 2 kHz frequency. If you back to our exercise here, this is our frequency usually. Our frequency is 4. Omega, based on physics, omega is the 2 pi f. F is the frequency. So from here you can figure out, right? For example, 4 equal to 2 times pi times f. You move the pi over there. The frequency is equal to 4 over 2 pi. Okay, so this exercise is just give you the this assignment. It gives you the frequency directly, 2.2 kHz. Okay, so this is what happened. So for the part one, this is what you should do. For the part one, you calculate the total impedance. You calculate the total impedance. I can give you a formula. The total impedance is equal to, you need to take the square root and square, R square plus XL, okay, minus XC. Square this, and then you follow this. The XL and XC, you can refer to my example here. It's right here actually. Right here is called the Z, right? It is the X. You can just type impedance for the inductor. On the search engine, it will show you the same thing here. Okay, so these two are the important the impedance for the L, impedance for the C. Okay, so from here, let's close down this one. I also close down this one. Okay, then you can cover part one, and then for the part two is to calculate the total current. Okay, so I can let you know also. You just take the current is equal to V over Z. Okay, so you know which one is V already. And the third part, because this question is quite straightforward, that's why I hope that in the final exam you can score it. The phase angle. For the phase angle, I think you can use the common one, the tangent, the inverse tangent. You can use this one. I'll give you a formula because this is quite common already. Okay, you can take the theta is equal to inverse tangent. Okay, then you take the XC, because this circuit comprises of three different elements. XL minus XC over R. Okay, because remember the phasor Z R XL minus XC. One more time, XL minus XC. That's why you have this reactant part divided by this one, the opposite over the adjacent equal to this hypotenuse. Okay, tangent. Number 4, calculate the voltage across each impedance. So what it means is the what does it mean, each impedance? It means each impedance, this one is one of them, 2, 3. Okay, so you need to find the voltage. I give you the first one. Okay, the voltage across the first impedance is equal to the current multiplied by the Z1. So where is Z1? Z1 is these two components. Yeah. Z1. This is Z2, right? Second impedance and the third impedance. So you need to calculate separately. Okay, because you have one common I, one common current. And then the last one, as I mentioned earlier on, the last one actually is a phasor for the impedance. XL minus XC, R, and Z, and the angle. You just calculate this value, then you fill it in, will be your answer already. Okay, that's all, guys. The question 2 is quite challenging. I have to agree. Question 2 is quite challenging, but I already have you 50%. Let me think about it. If I think you still need wait. This will be question number 3. Okay. If you still need additional help, I will post some to the WhatsApp group. So this is question 3. Okay, guys, that's all. I will share this one file with you. I'll convert to PDF file and share with you. Okay, so if you have any question, you can post in the WhatsApp because the time is already over. I need to prepare for Okay, bye-bye.